today, what I'm going to do is I'm going to cover some ideal filters, but before I do that, I have to do one thing that has to do with sampling. We've done the Fourier transform, and I introduced to you the DTFT. Now, how many know that you have to sample its signal at twice the highest frequency of interest? Didn't you get this in your laboratory? Not you. In your laboratory work somewhere? I'm going to show you why now. All right? Now, I'm going to do this in the way, I'm going to try to make this clear to you the way I would want it presented to me. I'm not going to touch on a lot of stuff that is not relative. Everything's going to be very directly related to that, and then we're going to talk about filters and ideal filters. So first, and you don't have to write all this down. You know this, but I'm just putting it up here as a reference. When we look at the Fourier transform, x of omega, it's equal to the integral from minus infinity to infinity of x of t here, e to the minus j omega t dt. And that marker is not very dark. And brand new. Let's try this one. So that's the definition of the Fourier transform. Do y'all agree with that? Now, when I said we're dealing with sampled signals, I say one way of indicating a sampled signal is just to say it's equal to x of t times the summation here of delta of t minus nts, where ts is really going to be the sampling interval. And by the same token, f naught would be 1 over ts, would be the frequency of sampling, and omega naught would be equal to 2 pi over ts. Or you could call it, you don't have to call it naught, you can call it s for sampling. Doesn't matter. But when we talk about this, this is from previous class. If this is t, and I looked at a signal here, x of t, then an example would be something where there would be uniformly spaced positions here, all spacing ts, and this would be like x of n, really, x of n ts, where ts would be the interval, and n would be an integer. Everybody follows that, don't you, class? A sampled signal. Now, what we said is, if this is a general formula for the Fourier transform, and this defines a sampled signal. This is what we're going to be using. We almost always, in this day and age, do digital filtering. We sample signals at a certain frequency, then we take that data and we quantize it and we digitize it, we store it. So try to understand where I'm going with a lot of this is applicable to everything we do in the modern era, digital filtering. Now, when I take that signal and I say that now I have the integral from minus infinity to infinity of this, where I have this right here, and I'm going to make this point. You all realize that these impulses only have non-zero values where t is equal to nts, correct? From before? And therefore I can replace this t with x of nt. So I can actually put this and make it the summation from n equals minus infinity to infinity of x here of nt times delta of t minus nts. Now this is a little trickery of sorts, but it's really not. I just brought x of t inside the summation because it only has values when t is equal to nts. Now if I put that in here, the summation, what I can do is this. I'm getting there. I'm developing the DTFT. I've done it before, but I'm just letting you see what I'm up to. Now I can say, when I look at this here, because this is NTS and not T, technically with me, I can take this integration and bring it in here. Bring it on that side, and then I'll leave the summation out. Do you all see what I'm doing? I'll do it clearly right here. Let me break it down this way. So now I can say that x of omega is now equal to the summation n equals minus infinity to infinity of, and now it's going to be x of nts times the integral from minus infinity to infinity of delta of t minus nts times e to the minus j omega t dt. I've pulled this out because it's not a function of t anymore. It's a function of n only, and ts is just the integral. Follow me so far? Work with me on this. I want to show you why this is important. Remember, that's continuous time. That's where we were. Now we're going into discrete time, but we still have an infinite number of samples possible. Now when I take this and integrate it, you all see that this becomes the summation of n equals minus infinity to infinity here of x of nts, right? And then, since this is just an impulse function, the only thing I do is evaluate the function next to the impulse where the impulse turns on or goes to infinity, right? You all see that that means I just have what? E to the minus j omega and then nts here. You all see that? How many do? Make sure you do. Right? Because the integral of an impulse is just one, but you have to evaluate the function that's next to it when it turns on at the point the impulse turns on or jumps, so it's at nts. So you replace t by nts. Yes, sir? Oh, now this is the classic DTFT, but what we do with the DTFT, we suppress the TS. So we say an actual definition for the DTFT is n goes from minus infinity to infinity, x of n, we're going to suppress TS, and then it's going to be e to the minus j n omega. Now, what you can glean from that is TS is suppressed, and when you look at this, omega TS is really capital omega. This will become useful later. And this is the definition of the DTFT. Don't worry, I'm getting to the point in sampling. But you have to know we went from continuous time, if you have a sampled signal, now we have discrete intervals of time, and that is the DTFT. Still, the extent of this is from minus infinity to plus infinity in n and therefore in time. Are you with me? In other words, it's not tailored down to something that is computationally observable, unless you can say for a large number, for all say n less than 0 and n greater than some large n, the function is 0. This is still one of these things that's fairly abstract. Understand? We're going to do a few of those in a second. But, now, hold it right there. That's the DTFT. We'll get to that in a second. Now, why do we need to sample at a rate of at least twice the highest frequency of interest? And this is the important one. I'm going to use this same integral here, right here. And I'm going to do something first with this. I'm going to say that the sampled signal, x sampled of t, is equal to really x of t, right? Times the summation of delta of t minus nts, where n goes from minus infinity to infinity. Do you all agree with me? Right? That's the sampled signal. Now what I'm going to do is this. I'm going to focus on this for a reason. And I'm going to turn that into a Fourier series. Remember, any periodic function can be turned to a Fourier series, right? Everybody know that? By the way, you got tested on Fourier series last time with the finding the constants. The impulse functions are given in this one, so it's a no-brainer getting the constants. But you don't have to take any derivatives. For this one, what does it really look like? By the way, this function is called a Comb function. And what it is simply the summation of delta of t minus nts equals minus
minus infinity to infinity. And what you get basically is this. You get a bunch of impulses, right? All the way up and down the axis. This is always going to have a spacing of TS, right? And that just goes on forever. Follow me? It looks like a comb if you think about it. That's why it's called a comb function. Now, that's periodic, and therefore this function right here can be rendered as a Fourier series. It can be rendered as n equals minus infinity to infinity of some c of n times e, right, to the j n omega naught times really t. Now, omega naught for this one is really the sampling interval, so it's 2 pi over ts. You can just put it like this. I didn't put omega s because that's the way you most commonly see the exponential Fourier series described, right, class? Now, how do we get c of n for this? Fundamentally, what is it? It's 1 over the period, right? In this case, ts. You all agree that it's periodic with ts, correct? And it's the integral. In this case, I can go from minus ts over 2 to ts over 2, because that's over a period. So I'm going to start, right here, and I'm going to end right here. Do you follow me? Just over a period. Starting at minus ts to ts over 2. I mean, minus ts over 2 to ts over 2. You all see this, class? I'm trying to get to the point, but I got to set it up right. Are you with me? Now, when we do this, that means I have only one function, right? I only have what? Delta of t times e to the minus j, right? And omega naught t dt. And what's that value going to be? What is c of n? 1 over ts times, when does the delta function turn on? T equals? 0. And what is e to the 0?
1.
1. So that's just 1 over ts, isn't it, class? Therefore, this whole series right here, this delta function series, that whole thing is just going to be the summation, really 1 over ts times the summation here, where n equals minus infinity to infinity of e, right, to the j n omega naught times t. Now, this right here is one of these things, this is a minus infinity. When I look at a sum of exponentials like that, to me, that doesn't look like it's going to go to a bunch of spikes. Do y'all agree with me there? You got a constant times an infinite sum of exponentials. E to the j 1 omega naught t plus e to the j 2 omega naught t plus e to the j 3 and so forth and so on. With me? You wouldn't think that it would go to spikes. I wouldn't either, but it does. That's all that matters, it does. Mathematically, that's true. And if you go to the math department, they have all sorts of people that love to talk about what happens when n goes to infinity, about all sorts of things. I'm not one of them. I believe it's true. We're going to move on from there. I need that to go where I'm going. Now I need to erase this, okay, guys? I need to, that portion of the board. I don't want to leave the DTFT up there. You'll notice I'm getting at the DTFT using the same basic thing, the basic definition of the integral, right, of x of t times e to the minus j omega t dt, right? Then I put in the sampling and I got the DTFT. I did the same thing with that, but now I'm going to do one thing different. Now all of a sudden, because it's sampled, I take the sampling right here and I define it as such. Now watch this. I'm going to try to get it all in this corner of the board. I'm going to leave that there. So watch. Now, I take the sampled signal, I'm going to rewrite it here. It's equal to x of t times the summation of n equals minus infinity to infinity of 1 over ts e to the j n omega naught t, right? Isn't that the series right there, class? Y'all agree with me?
Yep.
I just took that infinite series of spikes called the comb function, and I replaced it by the Fourier series representation, right? Now I do that, and I notice something. Really, this could be written as the summation. This is an n of, I'll put the 1 over ts out in front. And now I have x of t times e to the j n omega naught t, don't I? And that's x of s of t. Agree? With me? Come on. You got to see this. Don't you guys? Everybody see this?
Yep, can you say that again?
What I've done is, instead of having x of t times the delta function series, I replaced the delta function series by this. And because x of t is not a function of n, right? I can bring this, or I should say, yeah, I can bring this inside here. Isn't this exactly the same as this? Now, anybody want to take a guess where I'm going with this? Remember, my goal is to show you that you have to sample at twice the highest frequency of interest. I know there's at least one person who knows this, but he's reluctant to say it.
You're gonna plug in 2 over,
No, I'm not going to change omega naught to 2 pi over t,
Okay.
ts, but that's going to happen, but not yet.
okay.
Anybody? All right, now we look at this. And this is where we're going to do a simple Fourier transform. Now, this is called the special Fourier transform. I know this is periodic, but we're going to do it over one period. Actually, we're going to allow the Fourier transform to investigate this. Now, what is the Fourier transform of this going to be? I want you to think. It will go to what domain? X, S of omega, right? You all agree that TS is there. It stays there. Do you all agree with that? So now I get 1 over TS. Now I have a sum. Nothing changes with that sum. It's over n. But now, what is the Fourier transform when I have, if I have x of t go to x of omega, what does x of t times e to the j omega not t go to? Anybody? Yeah, that's right. X of omega, right, minus omega naught, right? Do you all agree with that? How many remember that? What happens if it's not an omega naught, if it's an omega naught? This becomes an omega naught. You understand? How many do? Now I come here, and the Fourier transform of this becomes a summation of x of omega minus n omega naught. Follow me? We're almost there. I'm going to go ahead at this point. I'm just going to say it's not omega naught, it's omega sample. All right, they're the same thing. Understand, class? I left it as omega naught because that's the way you're used to seeing that series written, aren't you? But I'm going to go ahead and put omega s in here. It's just a sample frequency. And now, I'm going to need some more boards, so I'm going to erase this. We have the DTFT. I'm going to get back to the DTFT in a second. But this is important. All this runs together, and this is the reason I'm choosing to do this. Now let's take a picture what that looks like in the frequency domain. I'm going to just assume a certain tailor-made x of omega. Suppose I say that my x of omega looks like this. And here is b, and here is a minus b. And that is just some constant a. It's a triangle waveform, and this is omega here. All right? With me? Now, that's x of t's waveform. When I get x sampled of t, what actually happens is what? Now I get the sampled waveform. This is caused by an x of t here. Now x sampled of t renders this. Now it's a summation, and it has the 1 over ts in front of it, right? In front of it of x of omega minus n omega naught. N goes from minus infinity to infinity. And what that looks like is this. Now I have a over ts right here. And then at omega s, I have it repeated. And then out here at 2 omega s, I have it repeated. And so forth. This is omega. Down this way, this is a minus omega s. It's repeated, right? And then down here at minus 2 omega s, it's repeated. Does everybody see what I'm showing here? That's in the frequency domain. This is omega. Now, what you see is this waveform is now just step and repeated up and down the axis with a scale factor of 1 over Ts in front of the A. And it almost looks like cosine modulation, doesn't it? Almost. Except there's an infinite number of these guys, right? Actually, you can do something tricky with this. I'm not gonna. You can turn that into a cosine series, but it doesn't serve a purpose to do it that way, single-sided cosine. I'm not gonna do it. I'm gonna leave it as this. But when you see this right away, what do you notice? This is what? This is at a frequency of B. This is minus B, right? Keep working with it. Where's this frequency? Right there.
Omega 1 minus B.
It's omega s, well, it's supposed to be s.
Sorry.
This is really going to be omega s minus b, right? Now what if all of a sudden omega s minus omega b put it down here? What would happen?
Not be good.
Well, then you get something that, nothing good, that's right.
Okay, so are these triangles actually touching or are they not?
Not yet.
Okay.
On purpose, I didn't have them overlapping. But this is what we don't want, right? Why don't we want it? Because if you get that, that's called aliasing. And it is bad. All right, horrible sound quality. Does anybody do anything with any of these things like, I can't think of it, it's not soundboard, any type of equalizer where you actually have sampled signals. You can, and you take a look at changing the actual like weights at a certain frequency so you get a, say, more treble or more bass. Do you know what I'm talking about when I say this? It's called soundboard or equalizer, something like this. Well, something else that they have probably on YouTube are things where sound engineers, they play around with the sampling rate and the highest frequency of interest. Now, your ear, supposedly, somebody who's young like yourself can hear at about 20,000 hertz. I know I can't. My nieces can, but I can't. But if you don't sample audio quality music at least 40,000 hertz, twice the highest sample frequency, then you get something called aliasing at the higher frequencies. And that's right here and here. Has anybody ever heard of aliasing or listened to it here? Jeff, you probably have.
Can you spell?
It's horrible. You'll hear and you'll hear it will completely destroy the fidelity. Now, what really it happens is this, and I'll show you this later, but I can take this signal as long as there's no aliasing, as long as there's no overlap, and I can completely extract the information up to the highest frequency of interest. I can take this waveform and do what's called a low-pass filter, so I'm just retaining this, and then I can take that and I can recreate X sampled of T completely, and I can get X of T, I should say even. I can get the X of T waveform up to the frequency, highest frequency of interest. However, if there's aliasing like this, I can't. Then everything's corrupted and it sounds horrible. All right, remember that. The reason is this. So, to prevent aliasing, put this down, to prevent
Can you spell the alias? I can't.
aliasing, all right, it's like aliasing.
That's what I'm.
Aliasing. Now, what happens is to prevent this, omega s has to be greater than or equal to 2 times the highest frequency of interest, or B. That's the highest frequency of interest. And that's so clear. Has anybody ever done any experiments with this? I mean, now they literally have so many digital tools where you can take and record yourself. You ever recorded yourself? And then you can take that recorder, even though it's stored digitally, and you can sample the thing at a speed below, say, 8,000 hertz. And then you can go ahead and do a digital filter and and try to extract that information. And it's horrible. You can't understand yourself. You'll hear echoes. Has anybody ever heard alias music, anything like that? Jeff, you surely have, I know you have.
Is this
Oh,
the-
yes, you're a musician, sure.
Yeah. Is this like kind of have to do with why phone, like,
That's echo.
call music?
I think you're talking about the echo.
Yeah, well,
It's not an echo.
okay.
It's garbled. Have you ever heard really garbled communications? That's what it's like. You should go on YouTube and just listen to aliased versus non-aliased music. It'll give you a shock. And you realize how bad it is. Now, I personally, in Radar, for instance, you're not going to listen to this stuff. In Radar, if you get an alias thing, I mean, it's basically the whole game's over. You're not going to see anything. You can't see anything. There's a lot of reasons. It's the highest frequency of interest. You have to sample it. Here's the downside of sampling. I just want to give this to you. This is something, you get this later. In Dr. Reeves' course, I encourage you to all take this. He has digital image processing and digital signal processing. You'll never regret taking it. You'll regret getting up at 8, but you won't regret getting the information. And I mean this. When you go ahead and you take a look at sampling, what do we have to do to sample? Suppose it's a microphone and there's a voltage coming out. We sample it, right? We're going to sample it, say, 40,000 hertz. Now, as soon as we sample it, what do you know? Now, if we have, say, 1024 places to choose it, we have what's called the dynamic range. Now we have to pick one of those that's closest to that and stick it in there, right? But that takes a lot of memory, right? Suppose we don't want 1024, we want 2048. Now there's a much higher dynamic range and more storage, right? And then maybe we want to double that. Maybe we want to get super high fidelity and go to 100 times that and store that. Well, now you get this huge amount of digital data that's stored, right? Now, if you do real-time processing, you're not only sampling at a certain rate, it's twice the highest frequency of interest. Now you're quantizing it so the quantization error is minimal, and it uses enormous amounts of data. I'm mentioning this because in Radar, we send out a pulse, it comes back, we sample it after we bring it down to baseband. We sample the thing, then we take it and we store it. And all before one called coherent processing interval. Now we have to recover all that information, do digital processing, and to present our finds on the screen. And it's an absolute monumental, I call it the most intensive kind of problem because it's real-time data processing. You can't use non-causal filters. It has to be all these things that are real-time allowable. And it'll drive you mad when you're trying to do this in the digital world. You can't recover all the data fast enough. Now, anybody heard of GPUs or graphical processing units or like CUDA coding? All you gamers, any gamers here at all? Well, you guys live in this world, don't you? You program your own, some of you. That's the game. If you can do that stuff really good and you understand the theory, you got jobs everywhere you want. I'm telling you. I always get pleased from some of my old students that are working with projects with radar analysis. Do you have any kids that are sharp with theory, signals, and systems in EMAG and also know a fair amount about programming, like CUDA card programming or gamer, I call them gamer programming. But if one of you guys turns out to do that, I got a job for you. I got a lot of jobs for you. But you have to understand the theory, so that's the bottom line. Now, back to the filter world. A couple other things before we move into the DTFT. Look this up, aliasing, when you get a chance on YouTube. Has anybody here done any kind of work where you actually took real live sound, sampled, and then stored it and digitized it, did any kind of like sound quality engineering on it? Did you? Did you do this for a band or where?
Yeah.
I'll just mention one other thing about audio quality. I don't know a lot about this. I'm not a musician or that level. But what you don't understand is even though your ear can only hear to 20,000 hertz, the very best of you, the truth is sometimes if you don't recover sound up to 80,000 hertz, you won't get the true impact on the actual, like the whatever it is, say Carnegie Hall or something like that. The reason is this: the high frequency sound that you can't hear, when it interacts with the media around it, will produce low frequency vibrations in that. You know, all the sounds in the hall that you'll never catch if you just sample at a low frequency you'll catch if you sample at a much higher frequency. Remember that. All right, just remember that the environment interacts with that sound too and produces secondary sounds that are at a lower frequency. So keep that in mind. And I'm not a guy that's going to do a lot of talk about the world of high fidelity sound and capturing an orchestra because I'm not a sound engineer. But if you, I know if you're a good one, you're going to make a fortune. That I do know, if you're a good one. Okay, now, next thing we're going to talk about, and this is something I'm going to expose you to without going through a lot of theory. I just want to make sure you understand it. It has to do with the ideal filters and how come you need something called a phase, a progressive phase shift in an ideal filter, so it will reproduce everything without any kind of garbage. Let me go ahead and do this. Now, don't write anything. I'll tell you what to write. Just listen. Now, you know, if I have any x of t, and it's periodic, right? It can be basically rendered as this: the summation of some c of n e to the j n omega naught t, right? N equals minus infinity to infinity. That's the exponential series, correct? It can also be rendered as a cosine series, and that means you would have some c0 plus the summation from n equals 1 to infinity of 2 times the magnitude of c of n, right? Times cosine of n omega naught t plus the phase angle of c of n. All right. Either one is equivalent. This one is important for a lot of reasons. It looks like a phasor. Each term, as n goes from 1, 2, 3, 4, looks like something you can put into a phasor form very easily. Magnitude and angle, right? With the frequency being n omega naught. Now, if we take this and we put it into a filter, this system. So I put this thing into a filter. I have C0 plus the summation n equals 1 to infinity of 2 times the magnitude of c of n cosine of n omega naught t plus phase angle of c of n. You don't have to write this yet, I'll tell you. I'll give you a good heads up when you write. This is just from up there, and we've had this. That's going to be my x of t. I plug this into a filter. Some h of omega. I could put h of t, but it's not relevant right now. What comes out that I showed you before, you all remember me doing this? I went and I put it in the frequency domain, then I assembled back the characters back in the time domain. When all is said and done, we got this. We got my y of t in the time domain was equal to h0, the transfer function here evaluated at 0, times c0, plus then the summation from n equals 1 to infinity of 2 times magnitude of c of n, that's the original signal. Then it has the magnitude of the filter response, h of n omega naught. And then it's going to be cosine here of n omega naught t plus phase angle of c of n plus phase angle of h of n omega naught. Now, that is the output in the time domain. You all remember that? You may not remember the exact method I used to get every one of those, but how many remember that? Here's what it really is. I take each of these terms and put it into a phasor. I have a magnitude of 2c of n. I have it in an angle of c of n. That goes in. It's multiplied by the transfer function. Output comes transfer function times 2c of n at a certain phase angle, right? Bring it back in the time domain. I have to multiply that by e to the j n omega naught t and take the real part. When you do all that, this is what you do. Very important. Now, I'm going to tell you one thing. If you put x of t in here and that's y of t, for a linear system, for something that's a linear time invariant system without distortion, then if I put x of t minus some tau here, I must get a y of t here. Then simply y, I should say, I should get a y of t response here. That feeds in, right? Then I must get simply y of t minus tau. Y'all with me? Time delay here, it just delays the output. With me? Without any phase distortion. Now you'll see what I'm talking about in a second. What I'm going to do is just take two terms of this cosine series and stick them in. And I'm going to show you why you're going to need this progressive phase shift that I'll talk to you about. Remember, h of omega here, I haven't given you any phase shift information yet, but I'm going to show you why. Now, if I take this, and I just said there's two terms, I have some A1 cosine, just call it omega naught t, all right, plus some, I'll call it alpha 1 for the phase shift. That's the first one. And there'll be some A2 here, cosine, of, call it omega 1t plus alpha 2. Omega 1 could be 2 omega naught, doesn't matter. This you write down right here. Write this down. Now, if this is the signal right here, and this is fed into that system, and I have my h of omega here, my output y of t will be equal to A1 times magnitude of h evaluated at omega naught times cosine of omega naught t plus phase angle of, or plus alpha 1, I just left it as alpha, plus alpha 1 and then plus the phase angle of h of omega 0 plus A2 times magnitude of h of omega 1. I suppose I should leave that 0 and 1 too, but that's okay. Times cosine of omega 1t plus alpha 2 here, plus phase angle of h of omega 1. Now just write that down. You all agree that that's the output? I simply take the magnitude of h, right, in front of that cosine business, and then add the phase right there, right? Agree. Keep watching. Now I'm going to do something. I'm going to go ahead and I'm going to factor out, when I take a look at this, let's do that. I'm going to say that this y of t is equal to A1 magnitude of h of omega naught times cosine of omega naught quantity t plus, and then this quantity alpha 1 plus the phase angle of h of omega naught over omega naught plus A2 magnitude of h omega 1 times cosine of omega 1 times t plus alpha 2 plus phase angle of omega naught, or I'm sorry, phase angle of h of omega 1 all over omega 1 I'll tell you why I'm doing this. I'm going to make it easier. I'm going to simplify something once you write it down. So really, I can do this part entirely so it doesn't confuse you. I'm saying I got a system. I'm feeding this into the system. This is my transfer function. This is what I get here. That's the raw sense. And what I'm doing is factoring out the omega naught here. You all see this? With me? Now, when you take a look at this for a second, you'll notice something. That the input signal was this, and I could render this, you don't need to write this down, but I can say that's A1 cosine of omega naught times t, right? Plus alpha over, alpha 1 over omega naught, plus A2 times cosine of omega 1 times t plus alpha 2 over omega 1. Now I did this for a reason, because generally speaking, if you have the function x of t, or any function where you have x of t is equal to something, say, cosine of omega naught t plus a phase angle, you can always render it as cosine of omega naught, and then it would be t plus alpha over omega naught as such. All right? And what you can see is that this looks like the form where you have omega of t plus or minus some tau. In this case, it's a plus tau. Do you all see that, class? That looks like a delay, and is in fact the phase is a delay. I can make this phase go to 0, and I'm going to do it right here, and then I'm going to change that. Don't write anything yet. I'm going to just change this to make sure you see that that phase is basically a time delay. If I get rid of that, then I get rid of this, and I get rid of this, I get rid of this, and I get rid of this. If you don't see it all yet, just hang on. I know this is going to be irritating to some. Are you with me? Now, for non-distortion to occur, this time delay has to be the same as this time delay. Remember, these represent just two terms in an exponential series, or cosine series. Are you with me? So this isn't equal to this. Then we got a big problem. Follow me? Because think about it, that's only two terms. If we put in a series, and here I got rid of the actual phase right there, right? If we put in a series like that, and the output all of a sudden starts having a different time delay for each frequency component, then you get complete garbled information. Just understand that. That should make sense to you. So the only way that you're going to get non-garbled information is if this and this are the same. Understand? And the only way those two things will be the same is if h of omega, all right, can be rendered as some magnitude of h of omega and a phase angle of e to the minus j omega times tau. Now that omega right there is the omega that the actually filter is going to filter or be operating at. So if it's omega 1, it'll be omega 1. If it's omega 0, it's omega 0. And then you'll see that these phase, this and this will always be the same. And that's why you have to have this progressive phase shift like this. Understand this, class? That alpha is any way, I mean that tau is any way to go. It could be 1, it could be 5, it could be 100. As long as it gets the same exact phase, it's a proportional phase shift. So if you're omega naught, say it gets a phase shift of 10 degrees, 2 omega naught, 20 degrees, 3 omega naught, 30 degrees, and so forth. Understand? It has to have the same progressive phase shift or you'll get garbled information. It's a little better to see this actually worked out in a problem. I'll probably give you one like this, but it's important now that you remember that. So please remember this. For a filter to have no distortion, for a linear time invariant system, there has to be the progressive phase shift like that. In all filters, and I don't have time to prove this right now, like RLCs and stuff circuits, have that in it. It's built in. So any filter you make with RLs and Cs, there's probably some crazy except, generally speaking, they're almost always non-distortion filters. The filters that can bring distortion are non-linear filters, and they do all the time. More of that comes later in the career and later in this course. Now, getting back, after I covered that, I had to touch on those two topics. Sampling and the need for a progressive phase shift so you don't have any kind of distortion. Then, what I do is this. Now, I get into two other things. We were talking about the DTFT. The first thing you're probably thinking about, what do I really need to know about the DTFT since I know the Fourier transform, right? First, the DTFT is an infinite series still. We've got to go through some simple pairing, and here's why you need to know the DTFT, because where we're going with this are going to get something called the DFT. It's discrete Fourier transform in the FFT, and they're used all the time on real data. That's why I'm saying it's important. I'm even going to show you the peak right now where we're going, and then we need to do something. When we have the DTFT, that is equal to x of capital omega is equal to the summation n equals minus infinity to infinity of x of n times e to the minus j omega n. One of the things about that, it is periodic in 2 pi. So this is periodic in 2 pi. Every 2 pi. Here's what I mean by that. If you looked at a DTF from, say, the DTFT for something that's exponentially decaying, it does this generally. But then, this is 2 pi, you would see it repeats itself. And this is 2 pi, this is 3 pi. It'll do this. Down here, it'll come. And it'll repeat itself every 2 pi. Do you follow me on that? And the reason is this, just look at this term. Go ahead and add 2 pi to that. What is e to the j 0? Anyone? What is e to the j 2 pi? What is e to the j 4 pi? 1. Adding 2 pi to e to the j omega always brings you back to the same point. Do you understand, class? Anytime you bring, and therefore this thing, without me going through a long proof, is always periodic in 2 pi, which means the only thing you really care about is the information from minus pi to pi. And some people will say, what about from 0 to 2 pi? Well, that's the same information. You can go from 0 to 2 pi if you're so inclined, but from minus pi to pi, it's symmetric at least. Follow me? For most things. So I like that. So now, what are the transform pairs you need to know? I'm going to tell you, we're almost there when we turn this into now a finite series and something we can really get our teeth into and see how it applies to real data that's analyzed. You're about there, not quite. So now I need to, because it's been a test and stuff in the weekend, I need to go ahead and just make sure we can do some basic DTFT operations. Now, in your book, I don't have my book, what page are the DTFT tables on? They have Z transforms that are related, but DTFT is something. Have you had this, by the way? Anybody? Did you have this, DTFT? I know you've had it. You don't count anymore. You're retired. Anybody? DTFT tables? It's discrete time Fourier transform tables. No? No book? You see it? It should be buried in the Z transform tables. Well, if you find it, you find it. I'm just going to do this. I'm going to put them up here. This is DTFT tables. I'll give you some. Generally, if you have x of n, your DTFT is x of capital omega. Just remember that.
398,
All right, page 398. Thank you.
and there's also properties on 395.
All right. We're going to get. We use a lot of the properties from Fourier for this 395. Now, if that's true, the next thing I'm going to say is let's get some pairs, basic pairs. Didn't I say with Laplace transform and Fourier, you needed about 4 or 5 transform pairs, and then after that you just use properties, don't you? Isn't that right? You got to have the pulse. I mean, well, for Fourier it was pulse. You got to have what? Exponential decay. You got to have impulse. You got to have U of t, or I should say, yeah, U of t, and basically 1 had to go to 2 pi delta omega. Now for this one, there's some transform pairs you have to know. The first is delta of n. You remember what that went to? It's no surprise. It went to 1. You better put up, that is the DTFT, so you can look at that. And the next one was a to the n, u of n. Do you all remember that one? I showed you a little, didn't I show you the trick on how to do that one, or not? Okay, well, we'll do that one. Here's the DTFT, so now I can say that x of omega, if x of n is a to the n u of n, is equal to the summation of a to the n, right, times e to the minus j omega n, where n would go from 0 to infinity. The reason I didn't put from minus infinity to 0 on there is because of the u of n. Follow me, guys? See the u of n there? So, now, after that, what does that go to? Well, that series looks like what? It looks like a summation of the quantity A, right, times e to the minus j omega, the whole thing to the power n. N goes from minus infinity, or excuse me, from 0 to infinity, right? Here's a trick you're going to thank me for. This is one of those things you're going to need to know for the rest of, well, most of your time here at Auburn, for sure. You're going to graduate in engineering. If I have this series, I thought I put this on the board. A to the n from n equals 0 to infinity. Y'all realize that that's really what? 1 plus a squared plus da-da-da, plus a, let's not go to infinity, let's just go to capital N. A to the n. Let's do it this way. Y'all agree with that? We'll let that go to infinity, but let's just make it n. Now, if I take that and I multiply it by 1 minus a times that sum, I'm going to do you a favor here, you're going to like this. Again, I have this series right here, but I'm multiplying by 1 minus a, right? Now watch. 1 times that series is just that, right? It's 1 plus a squared plus da-da-da plus a to the n, right? With me? 1 times that. This is cool, you like it? Now, when I have a times a to the n, what do I have? I have minus the quantity a plus a squared plus a cubed plus da-da-da plus a to the n plus 1. Can you all see that, class? How many see this? What do you notice? 1 minus, there's not a 1 over here, right? So the 1's going to stay, right? A minus a, gone. A squared minus a squared, gone. A to the n minus a to the n, gone. But minus a to the n plus 1 is retained. So it's 1 minus a to the n plus 1. And that's equal to the summation of a to the n equals 0 to infinity. Now the 1 minus a I just put down here. And now, voila, we have solved the series. There's a guy named Gauss that will tell you more about it another time. Gauss was brilliant at this kind of stuff. He is one of my heroes, my really big hero when I was young. I'll tell you more about that later. Some of you may know. You know Gauss? He's one of the great physicists and mathematicians. That's how you solve that series. Now for this one, instead of quote a back there, you replace it by a minus e to the minus a to the e to the minus j omega. What do you see happen? If n goes to infinity, you get 1 over 1 minus a to the e to the minus j omega. Or you can render it as e to the j omega over e to the j omega minus a. Either one of those is correct. And I'll do this next time. I got a little behind, but I want to try to make sure I touched on the filtering business because it's so important. You're going to have laboratory work, which is really important to know that. And don't you have labs right now where you do filtering? How many of y'all have labs that do any kind of filtering work? Don't you? High pass, low pass, band stuff? Oh, you're past it. You should have some more where you have to extract data by developing filters. I think I'll give you some homework on this, and we're going to talk about the DTFT, and then we're going to hit DFT, and you're going to see a lot of stuff come together, why we're so emphatic about